Hi everyone. I hope you can hear me. Maybe if someone could just confirm that we are live and properly connected through the chat, it would be really great. Okay. No feedback. I hope everything is properly set up.
Yeah.
So we are together for about 30 minutes together. Just to start things up. There we go. Just to introduce myself, I'm Fabrice Devoise. I'm a Chief Technology and Innovation Officer at Smile. I have a past of real-time embedded development, Java architecture, and also mobile native apps development. And I've been a startup for quite some time. And now I'm really focused on pushing teams forward to the unknown. And trying to foster energies within the group to push forward the limits. And Anna?
Yeah, hello everybody. Anna was speaking. I'm working with Fabrice to reach this unknown, mainly on engineering, software engineering topics, and any kind of technology that we can leverage on. And I will help Fabrice today to cover this story.
Yes. All right. So just a few words about the innovation team at Smile and why we have developed this demo and this prototype. What we are aiming at is really introduce new technologies within the group for our co-workers to do a level up on their skills, but also bring this expertise to our customers and help them innovate. Our focus areas in the past years have been mainly on edge computing, artificial intelligence, which means machine learning and deep learning, but mostly turns toward computer vision and also NLU, NLP, so natural language understanding and processing, for mainly doing chatbots and conversational assistants at large, which includes voice assistants. If you want to know more about what we are prototyping on what we are doing currently, I encourage you to maybe scan this QR code, which will lead you to our Medium, which is medium.com/smileinnovation. I encourage you to see the articles that we regularly post, as well as the Tech Watch that we post about every 2 weeks with a digest of what we've seen that is interesting. But more than a team, an innovation team, it's greater than us. It's just not just us trying to push new technologies. We also include a huge network of partners on which we rely to bring new technologies, bleeding edge technologies to our customers. And it also allows us to adapt this technology to customer needs, because we've got privileged access to the technology and of these startups and ecosystem in general. What we do for our customers in these innovation teams, because previously I was talking more about what we do internally, but we also work together with our customers. What we bring to our customers is try to accompany them through their innovation journey. And it goes sometimes as early as doing ideation to generate ideas, to think about what could be an innovation roadmap for them and make it real. So it goes through different phases. It could be hackathons, it could be ideation workshops, and so on and so forth. And we can go down to innovation management, also do co-innovation with our customers, and we put innovation in practice in general with our customers. Now onto Warhol, because it's the theme of today's talk. What is Warhol? It's our code name for this prototype that we've built, for this demo that we've built, which uses a few technologies that we'll explain. Our goals on these projects were quite specific. First of all, we wanted to demo our capacity to innovate. This is the purpose of part of my team. So we wanted to have a project to foster energies, to create something that shows our knowledge, our know-how about innovation. Second, we wanted to show our capacity to make different skills converge, because Smile is quite big companies with very different skills, and we wanted to show that we are able to gather teams to work on projects together. Third, we wanted to show our capacity to integrate and create solutions, be solutions oriented for our customers, because what our customers are asking are not horizontal technologies or pure technologies. What they ask is a solution to their problem, and this shows how we can bring solutions from end to end, from thinking about what could be the solution down to what is the solution and deliver the solution. Four, we wanted to have a premium positioning thanks to a well-designed object, something that was seducing, appealing for our customers to showcase in events. And finally, we wanted something that was easy to transport with a plug-and-play usage. It means that we wanted people to only have to plug the power, and it simply works. So when you're thinking about using this kind of devices in events, in large events, large venues, it quickly falls short because of the network. Most generally, the Wi-Fi network is really slow because it's really crowded, and the best way that you can have a demo run smoothly in this kind of environment is really to have no network need. This means that we wanted to have something that was able to run on the edge. So this was the first constraint, technical constraints. Second, we wanted to use artificial intelligence and especially computer vision, because this was showcasing the work that we did in the past. And third, we wanted also to showcase our knowledge on natural language understanding and voice assistance. So we wanted to add these three specifics into our demo. Second, we had to find a topic. So if we wanted to have that topic, well, it was difficult to find something, an object that create an object that was able to run on the edge, brings added value, and use as computer vision as much as voice. So we ideated on that. We rapid prototyped the subject to see what could be the ideal object that we could build, something that was easily transportable and so on. And we went on to something that we called a food pairing device. And I will talk about the capacities of this device later on. Once we decided what was the purpose of this object, we had to define a user journey that mixes voice, touch, and computer vision. Maybe mixing voice and touch quite seem unusual, but in fact it is not. If you imagine yourself in a large venue, there is most of the time a very loud noise because of people talking, announcements, and so on. So capturing voice and understand what the people actually speak into the microphone, it's sometimes hard. So we wanted to have the user experience not fall short on this aspect, and still have the possibility to interact with the device and go through the whole demonstration without being stuck with misunderstanding about what the user has said and the voice comments. And for the computer vision, this was a basic requirement. But once again, I will explain the whole user journey later on. So we knew what we wanted to create. So it is a food pairing device. So we had to give it a shape able to support the various features, capabilities of the device. So it means capturing images, of course, capturing sound, and broadcasting sound through a speaker. So we had various hypotheses, various designs, and the one that we chose was something that was, in our opinion, the most representative of what we wanted to show as the Smile brand, as well as being able to dismantle the object for transport. So this is the device. As you can see at the top of the device, we've got a screen. Then you've got a capture 3D print to direct the sounds as much as we can to the microphones to have the clearest capture that we could. And at the bottom of the object, you see some kind of a plate where we put ingredients that we want to use for this food pairing. And this is captured with a camera that is hidden right below the microphone couple. And the object is not that tall. It's about 1 meter high. And of course, doing all this is not that easy. So we had to make quite a few tests in terms of hardware, the kind of hardware we could fit into this object. Also some specificities of particularities of the hardware that we were using. Let's say, for example, for image capture, it's a raw Raspberry Pi camera, so we wanted to see if the focus was right, if the angle of view was right, being able to make some major or minor adjustments for the exposure and so on. And finally, so to unveil what is the user journey for this device, because before Alain goes through the technicity of this object, so the purpose is to do food pairing. So we imagine a few paths in which the user could interact with the device, but the main path is simply you're in the supermarket, let's say, and you want to know what you can do. What you can cook with some ingredients. They say potatoes, carrots, this kind of ingredients. You just simply put these ingredients on the plate at the bottom of the device. Its capture automatically recognizes the vegetables or fruits that you've put, and offers you to do a few recipes. You select your recipe, and from there you can also interact with the device to ask for wine pairing. And then you will go through a voice interaction with the device to properly select the kind of wine you would like to pair with this recipe. Once you're done, you can go, of course, back and forth between the wine part and the food parts. It's not a problem. You can also interact using touch, as I mentioned, if you, in case the environment is too noisy, or in case you just simply don't want to talk into the microphone. And once this is done, you can ask for feedback and contact information, because as I mentioned, this is something that is dedicated for fairs and events. So we wanted to do a contact collection and also collect feedback from the user about this demonstration. And once this is done, it goes back to the beginning, and you can start a new demo flow. I hope this is clear, and I am handing the mic to Alain.
Yeah, thanks.
Oops. There we go.
Yeah. Regarding the hardware requirements, we have to think about the features we need to support. And as the first one, we need, as explained by Fabrice, to support food items identification detections. And for that, we will rely on some deep learning logics. And it's important to have a bit of understanding of how it works, and just a simple quick refresh about these principles. Deep learning techniques rely on two main steps. The first one is what we call the training. You need to train what we call a model. A model is what will be used afterwards to detect the objects you want to detect. And to support that, you need to train this model. And what is training is basically feeding this model with a lot of pictures. If we are speaking about computer visions or video, in our case, it's pictures, of what you want to identify. So you need to build a kind of data set of pictures that will match what you are looking for detections, and to train this model. And after this training, you will get models that will be used on the device for the edge principle, so not connected to anything. And the software that will run on your device will use this model to transform pictures you capture with the camera into something that will be a list of food items you have identified. So what it means that we need hardware that will be capable of running this deep learning inference, so identify food items in a picture. And for that, you have either the choice of running it through the CPU of your device or using some dedicated accelerator. The first choice is, yes, basically running on the CPU of your device. In our case, we choose to use a Raspberry for the power consumptions, for the form factors, for the fact that the object is quite small, and so on. But the CPU of a Raspberry is quite slow for computer vision, and especially because also we want to use this device to run other software parts like the UI, like the voice assistants we will speak about afterward. So this is not the right choice for this kind of task. On the other hand, you have a lot of devices available on the market that are coming from NVIDIA, Google, or Intel, or the brands right now. From NVIDIA, you can have some kind of nano computer that looks like a Raspberry, but that contain some hardware specialized in running deep learning models. In our case, we did not choose that because this kind of device is quite big, can get things out quite quickly. The software integration is quite complex, so it's not the first choice of our. On the other side, you have USB dongles that are quite easy to use, quite practical because you just plug it on the USB port of the Raspberry, then, and you use it with a library that will be able to send the computation through this USB dongle. And we choose to use the Google one because integration with TensorFlow is very smooth and easy to use. So at the moment of this device conceptions, we choose to use the Google Coral device. Of course, we have also one important thing to support is the sound capture, the voice capture of people trying to interact with the tool, with the device. And for this kind of task in a crowded environment like the events Fabrice mentioned before, we need something that is able to capture correctly the voice. That's why we choose this kind of add-on that you can plug in on top of the GPIO of the Raspberry, which is a small card with 7 microphones capable of using these 7 microphones to transform in 1 sound waves to be analyzed for the sound for the voice assistants. Also, it has a native integration with Linux and Snips, which is a framework we use for voice assistants. At the end of the day, when you build all the piece of hardware together, it looks like that. It's quite simple. The Raspberry is the heart of the device, which is going to contain all the software we'll describe afterwards, but to which we will have connected the Google Coral dongle, USB dongle, all the I/O for pictures, so the camera, and the sound, so the matrix voice. And for user feedback, we will have also a touch screen connected to the HDMI port of the Raspberry Pi, and a simple speaker connected to the audio jack of the device. Regarding the software, just to recap what we need to do, and as explained by Fabrice, we need first to be offline and plug and play. So this is very important to match the expectation for this device. Second, we need a graphical user interface to have a feedback for users, but also to allow them to interact with the device in parallel of voice command, but also to be able to execute voice command, so the voice assistants. So we need software that will be able to support that. And finally, the deep learning inference. So we need the software stacks that will be able to use a model that has been trained to transform a picture captured from the camera into something that looks like a list of food items. So what we did is basically build a custom-made app for the user feedback, and so the graphical user interface in kiosk mode based on Electron JS and React.js. That will be the, let's say, the orchestrator of this device. Everything will be managed by this app. And connected to that, you will have the Snips voice assistants that is supporting custom skills. So what you want to command and execute or to manage the understanding logic of your voice assistant, that will be based on Python scripts. And also for the deep learning side, we just built a Python daemon that will be in charge of capturing image and transforming it into food items through the deep learning model. So if we summarize that, it's a simple architecture with a local MQTT bus to coordinate all actions between these three software components. Snips voice assistant is natively using MQTT messaging to support events through its assistance logic. So we just reuse this simple logic to coordinate all action between the deep learning daemon and the user interface, where we will have user interaction and feedbacks. So we just defined a dialogue logic between all these items to support actions and to support the feedbacks messages. If we go back to the deep learning topic, so what we did is basically what I explained from the theory phase. We had to find data that match our task goal, which is to identify food items. We focused on vegetables, so we had a set of fake plastic vegetables to play with during the demo, but we used real pictures from different kind of data sources, either well-known data deep learning database on which we filter out all vegetables pictures, but also from public image database like Google Image or whatever else. So it means that from all this information, you need to classify them or annotate them. So it's basically adding metadata to the pictures. That will allow us to go through the second step of the learning phase, which is data preparation. So it's somehow packaging all this information in something that will be compatible with the model that we will train, which is a third phase. So we train this model by feeding it with the data sets. Your data set is split into several elements. One that is containing the training data, and one subset part which is validation data. It's a bit of like doing a test on the model, but it's an important phase to making sure that the quality and the accuracy of your model is enough for what you're looking for. And the final step in this learning phase is to transpile the trained model into something that is compatible with the device you will use. So the Google Coral USB dongle. So you have a small tool that will transpile the trained model into something you can fit on the Raspberry to be used by the software. And yes, the final goal is to infer. So it's basically to use a picture that will go through the software to be transformed into information used by the device. Some numbers about these steps. You need a lot of data to train a model. So for this demo we had we choose 10 objects categories. So like I say here, potatoes, mushroom, tomatoes, and so on. On about 1,000 pictures per category and about 5,000 labels per category. So it's a lot of information to manage and to organize. And this is a minimal amount of data you need to get something accurate enough for what we were looking for. So we would add more pictures, more information, the model would have been better. And the training steps when you train a model, so we use a technique named transfer learning. So it means that you do not start from scratch. You start from a model that is already trained on other kind of objects, and you leverage on this already trained model to go faster. But even if you go faster, it's already something like 15 hours of training to get your model ready to be used. And at the end of the day, when you use a model, an inference is quite fast with this dongle. It's less than 20 milliseconds when you go through the inference algorithm. And by comparison, if you use a CPU from the Raspberry, it's more than 5 seconds. So it's the hardware acceleration is very important for this demo. Just an example of what these things we are doing. So in this video, you don't see a Raspberry, but a Coral development board, because we are doing the rapid integration here. But the Coral dev board is the same as a dongle, meaning that the software you develop on this card can be copy-pasted, and the Raspberry at the end, it will do exactly the same, with the same performance. Oops.
I think we are at the end.
Yeah, a few raw shots of the integration work, where you can see the different components we were integrating and testing for this device. And a screenshot of the app that we are running on the screen of this device. Yeah.
Yeah. Okay. So that's it. We've got 3 minutes for questions if you want. I had one question on WhatsApp asking can it detect software food ingredients for a soup. So yes, of course you can as soon as you can detect a tomato, you can detect that you can do a tomato soup. Yes.
Yeah. So this part is just a simple logic about we have a set of ingredients, and if we have in the recipe list something that match, we will display the recipe. So if it's soup, it will be a soup.
Yeah, maybe something that we didn't say, I don't remember, but I don't know if it was really clear on the video, but that's the hardware that we are using is capable of inferring for up to 120 pictures per second. So it means that it's pretty fast and pretty reactive in this respect.
In the user journey, video was not something necessary. Pictures capture was enough for the scenario, so we just rely on pictures. But yeah, in the video in demo, we were using a video stream to test the model.
Yeah, maybe one other additional information for those who know what we used, the brick that we use for voice recognition and natural language understanding is called Snips, but it has been acquired by Sonos something like 2 years ago. So now it's more closed source components and not usable for public, but we are doing some tests on other components such as Pico Voice and other bricks. So this is something that we are currently seeing to replace. All right, I think we're running out of time. Thank you very much for listening. For those who were together with us today, the video record will be available, I think, sometime soon. Anyway, thank you very much for listening, and have a nice day.
Thank you very much. Bye-bye.
Bye-bye, Anna.